Hello and welcome. In this video, we're going to look at how to calculate the RLC series bandpass filter. In this case, we have our input voltage over here on this side that comes straight across our linear resistance, and then it hits this parallel bar where we have a balanced LC component down here at resonance. This is going to stop our resonance frequency from entering ground. Right? It's going to back it up and allow it to go towards our output voltage. And so this is going to be called a bandpass filter, because it passes frequency at our resonance. So the first thing we need to do is set up our center frequency. So we'll say that our F center frequency here is equal to 1 over 2 pi. That's talking about a frequency there. And then our time constant, since we have an inductor and a capacitor, we're going to use our LC time constant of square root L times C. We can plug that in because we have all those values. So we'll say 1 over 2 pi square root of L, which is 1.6 millihenry, so 0.0016 multiplied by our capacitor of 0.062 times 10 to the negative. We see that that is micro, so we'll say 6. So this gives us a frequency here of 15,979 hertz. They want it in kilohertz, so we'll move that forward 1, 2, 3, and we'll say that we have 16 kilohertz. Round that up. 16 kHz. Right, and that's because the 9 and the 7 there are going to round up. So 16 is our answer for our frequency. After that, we need to figure out our bandwidth. Our bandwidth is going to take a couple of steps here. So we know that the bandwidth equation, BW, is equal to our frequency divided by our Q. And we don't have our Q right now, and so we got to figure that out. So our Q is equal to our inductive component, XL, divided by our total resistance, in this case, or our linear components. And so our RT is going to be on bottom there. And that's because we have no choice but to go through the resistor and the winding resistance to get there. So we need to put in the total resistance that we have. So we're actually going to add the resistors together there and combine them. So we don't have our XL value though, but we did just find our frequency. So we'll say that XL is equal to 2 pi FL. Let's send this out. We'll say that we have 2 pi times our frequency of 16,000, multiplied by our inductor value of 1.6 millihenry, so 0.0016. That gives us 61. So we'll set this out. 161 ohms. Now we know what goes on top of our Q is 161 ohms. We need to know our total resistance. Our total resistance is going to be the sum of those two resistors, so 33 ohms plus 0.56 ohms. We'll put that in on bottom there. So 161 divided by 33.56, with those two added together, we get an output Q of 4.8. We'll round that up. 9 rounds to 8. So we can go down to our bandwidth now, and we can say that our frequency was 16,000 divided by 4.8, which gives us our bandwidth here. 16,000 divided by 4.8, 33. That's in hertz. We want it in kilohertz. We'll move it forward 1, 2, 3. We'll say that we have 3.33 K hertz. All right, so that is our second value there, 3.33. And now we just need to go after our voltage output. And so the voltage is going to depend on the fact that we have two components here that are going to cancel each other out. Right, so since they're in series with each other, our inductive and our capacitive loads will cancel each other out, and we're just left with a linear load, which is our resistors in series with each other. And so that's what we're going to calculate, and we specifically want to know our voltage output, so we want to know the voltage drop across our winding resistance only. So we'll say that we have our want on top is our winding resistance divided by our main resistor plus our winding resistance, and then that whole thing is multiplied by our voltage in. And this is going to be our V out here. So we can plug that in. We know that our winding resistance is 0.56 divided by 33.56 when we sum those together. And then we'll multiply that whole thing by our input voltage of a millivolt value, and we can leave it in millivolts and get a millivolt out. Right, so 190 millivolts gives us 3.17 millivolts, 3.17 MV. And that should be our answer there. So let's type that in, 3.17, and we will check it. All right. Let us know if you guys have any questions.